We are now going to begin our discussion on improper integrals. Up to now, we have required definite integrals to satisfy two properties. First, the domain of integration. We always have closed or finite bounds. Secondly, the range of the integrand being whatever we are integrating, must also be finite on the given domain. So as we are working, we may encounter problems that fail to meet either one or both of these conditions. So for example, considering this first, we know there's a horizontal asymptote. So we approach infinity, this is never really going to stop decreasing, or it won't reach a finite value. The domain of this function is not a closed interval, it's infinite. It goes from 1 inclusive to positive infinity. So in all three of these pictures we have here, it would appear that the domain is infinite. It's not a closed domain, and that's due to some horizontal or vertical asymptotes. And you may think to yourself, well, we can't find the area of something that doesn't stop expanding. However, we're going to find that in all three of these, they all have a finite area under the curve. The answer is going to be yes, they have a finite area. So let's talk about infinite limits of integration. Let's consider this function, y equals e to the power negative x divided by 2. And the way this graph looks is drawn over here. I've graphed this for us. The area that lies under the curve in the first quadrant is what we're going to be looking at. And you might think this region has an infinite area, but we are going to see that the value is finite and that it's actually 2. So it appears to have an infinite area, but we will be able to determine a finite value. So we're going to assign a value to the area in the following way. First, we're going to find the area of the function a of b, of the portion of the region that's bounded on the right by some invisible value extending off to the right here, b on my graph. So the first thing we're going to do, let me write that out, is we're going to find the area a of b. So this is a portion bounded on the right by b. So in this case, a of b is going to equal the integral from 0 to b of this function e to the negative x over 2 dx. In order for us to integrate this, we do a u substitution. I'm going to let u equal negative 1/2 x. du is going to equal negative 1/2 dx, or rather negative 2 du equals dx. So skipping over the intermediate calculation, we're going to end up with negative 2e to the negative x over 2 from b to 0, which will simplify and give us negative 2e to the negative b over 2 plus 2. So this represents the area from 0 to b, some undefined value on the right. Our next step here, the second step, is we're going to find the limit of a of b as that b value approaches positive infinity. So the limit as b approaches infinity of a of b is the same as the limit as b approaches infinity of negative 2e to the negative b over 2 plus 2. So if I evaluate this limit and I'm to plug infinity in, I've got negative 2e to the negative infinity over 2 plus 2. Well, e to a infinite power, right, and that's a negative power, essentially that's 1 over e to the infinity, so that's 1 over a very large number. This term goes to 0. So I've got 2, or negative 2, times 0 plus 2, which is 2. So what we can say, therefore, and I'm going to define the rule in a minute, but therefore the integral from 0 to infinity of e to the negative x over 2 dx is equal to the limit as b goes to infinity of the integral from 0 to b of e to the negative x over 2 dx. So in that case, both of those are equal to 2. So this that I've written here is an example of an improper integral. This is an integral with an infinite interval of integration, or infinite bounds. And we can show that it is a finite value of 2, which is what we stated in this picture over here. And essentially that's a little bit because it starts to converge to 0. And so at a certain point, we're adding smaller and smaller numbers, and it doesn't affect the value of the improper definite integral there. So when we start to be adding values that may be getting larger, that is divergent. So let's look at the specific definition here. The example we just looked at was an improper integral of type 1. And you can see that we have 3 types of integrals here. So we have a situation where the function is continuous from a to infinity versus a function is continuous from negative infinity to some b value, or a function is continuous from negative infinity to positive infinity. And so all of these situations, all of these different integrals involve taking the limit as a certain value as b approaches positive infinity, or my a value approaches negative infinity. And then when we have both positive and negative, it's essentially part 2 plus part 1. So in each case, if the limit exists and is finite, we can say that the improper interval converges to a specific value, and that the limit is the value of the improper integral. And if we fail to have a limit that exists, we say that the improper integral diverges. It does not go to a specific value. So again, that's the definition of how we deal with improper integrals of type 1. And we're going to do some examples in the videos following this that will show you how we deal with each one of these 3 different types.